Have you ever wondered how engineers and technicians actually see the invisible world of electricity, to figure out what's going on inside a circuit? Well, today we're going to unlock that essential toolkit. You're about to find out how it all works. All right, let's just dive right in. Instead of me just listing a bunch of boring tools, we're going to put you right in the action. I want you to imagine it's your very first day as an electronics technician. So you look down, and there it is, a circuit board on your bench and a really clear mission. Figure out if this thing works and what exactly it's doing. This is your first challenge, and honestly, success is going to depend on knowing your tools inside and out. So, where do you even begin? Well, you start with the most fundamental piece of kit on the bench. This is the first tool you should always reach for when you're meeting a new circuit. This is the multimeter. And a great way to think of it is as the stethoscope of electronics. Seriously, it's your first-line diagnostic tool for just checking the basic health of a circuit, letting you kind of listen in on its fundamental properties without even having to power it on. The really cool thing is that this one device lets us answer 3 critical questions right off the bat. First up, continuity. Is there a solid, unbroken connection from point A to point B? Then, resistance. How much is the circuit pushing back against the flow of electricity? And finally, you can do a quick component health check. For instance, is that little diode on the board actually doing its job? Let's just focus on that diode test for a second, because it's a perfect example. A diode is supposed to be a one-way street for current. That's its whole job. A quick check with the multimeter tells you if that street is open in the correct direction and, just as importantly, closed in the other. If it's blocked both ways, or worse, open both ways, bam, you found a problem instantly. Okay, so our first health check looks good, the circuit seems healthy, the connections are solid, but it's just sitting there. It's inert. It needs a reason to wake up. It needs an electrical heartbeat. And here's the thing, a lot of circuits don't do anything on their own. They're just passive. They need a specific input signal, that heartbeat we were talking about, to even start doing their work. But what if you don't have that signal? Well, you've got to make it. And this is the perfect job for the function generator. I mean, think of it as a synthesizer, but for electricity. You need a smooth sine wave? Done. A sharp, digital-looking square wave? No problem. A ramping triangle wave? This device can create pretty much any signal you need, allowing you to feed your circuit the exact diet it's designed to process. Okay, so we've used our function generator to give the circuit its heartbeat. We're sending a signal in. But that leads to an even bigger, more fundamental question, doesn't it? You've dialed in a signal on the generator, but how can you be sure that the heartbeat you're supplying is what the circuit is actually getting? I mean, how do you look inside the wires and actually see the shape of that voltage as it's changing millisecond by millisecond? And this is where the real magic happens. The oscilloscope is our window into that invisible world. It takes that crazy, fluctuating electrical signal and it draws a picture of it in real time. Voltage goes up and down, time goes left to right. For the very first time, you can literally see the signal. But getting a clear picture isn't always automatic. You have to understand the scope's key specs. So for example, bandwidth. That tells you the fastest signal you can look at before the picture gets all blurry and distorted. Resolution is kind of like the pixel count on a camera. It defines how much tiny detail you can actually see. Accuracy is just what it sounds like. How much can you trust the measurement? And this one's huge. Input impedance tells you how much the scope itself might be interfering with the very circuit you're trying to measure. It's like the observer effect, but for electronics. And that brings us to a super critical lesson that every single technician has to learn. Your tools are incredibly powerful, for sure, but they are not perfect. They have limits, and being a great technician means knowing what those limits are. This quote from our source material really hits the nail on the head. It says that because a scope has a finite bandwidth, it can't perfectly capture an instantaneous or transient pulse. So, what does that actually look like in the real world? Just look at this comparison. On the left, that's the real signal, a perfect digital pulse with these razor-sharp 90-degree corners. But look at the right. That's what a scope with limited bandwidth might show you. The corners are all rounded off, the signal looks slower. So the bottom line is, if your signal is faster than your scope's bandwidth, the picture you're seeing isn't the whole story. So let's just step back for a second. It's the end of your first day on the job. What have you learned? Well, you've gone from a totally dead circuit on a bench to a full-blown electrical investigation. You've unlocked a really powerful workflow, right? You started with the multimeter for a basic health check. Then you brought the circuit to life with a signal from the function generator. And finally, you made that invisible signal visible with the oscilloscope. And you learned to trust what you see by understanding the tool's limits. That is the core of electronics diagnostics. The big takeaway from your first day is this. With the right tools and an understanding of their limits, we gain this incredible power to see and understand the hidden forces that run our modern world. It kind of makes you wonder, doesn't it? What other complex, invisible systems are out there all around us, just waiting for somebody to build the right oscilloscope to finally see them clearly?